So far what we've been doing, we call the single program multiple data pattern. And this is kind of the workhorse of traditional parallel programming. In fact, I think it's safe to say if you look at the last 30 years of research in parallel computing, the overwhelming majority of parallel programs out there that you hear about use the SPMD pattern, particularly in scientific computing. But there's another way to go about things, because in the SPMD pattern, every thread is redundantly running the same code. But there are times you want to take a single construct and share it out across the threads. We call this worksharing. And worksharing is an extremely important feature of OpenMP. And so we're going to talk about that right now. Now, in OpenMP, we have a collection of worksharing constructs. There's a worksharing loop construct. There's something called the sections and section construct. There's the single construct. And then there's also tasks, which technically aren't work sharing, but they act like work sharing. We're going to talk about those later. Right now, we're going to talk about the most common work sharing construct, which is the loop work sharing construct. So here's what the loop work sharing construct looks like. So in this code right here, you can see that I have pound pragma OMP parallel. Remember, if you don't see that pound pragma OMP parallel, there are not multiple threads. So I still have to create a team of threads. And so now I enter in the structured block, which is that parallel region, and now I have a for loop. And what I want to do is I want to split up iterations of that for loop to different threads. But I don't want to do all that messy stuff by doing it by hand, by saying, what's my thread ID? How many threads are there? The cyclic distribution like I was doing before. I don't want to do any of that. I just want to say, compiler, will you please take this loop and split it up between a bunch of threads? So I do that with pound pragma OMP4. All right, so that's saying take the immediately following for loop and split up its iterations between threads. And that's what this does. So it's a very simple construct. Now, I want to motivate this for a moment with an example. Back long, long ago, when we were first creating OpenMP, there were people working with us who said, you know, with the parallel region and those runtime routines and the synchronization, basically what we've talked about up till now, that's all you need. Stop. Because we want OpenMP small and simple. You don't need anything else. Well, they're kind of right. All right? Look at these examples. So I have probably the simplest loop I could think of. This is just a vector addition. Take a vector A and replace it by the value A plus a vector B. All right, so this is a very, very simple loop. Okay, I can go through using the SPMD pattern, and I can parallelize that. Here's the code. You can see it. Probably at this point, you can easily read it and follow it. It's the SPMD pattern. I pick a beginning index of a region, a closing index of a region, and then I give each thread that little region in the loop. So I can do that with the SPMD pattern and look at all the code I had to write. Or I could just do pound pragma OMP parallel, pound pragma OMP4, and I'm done. So now I ask you, which one of those would you like to write for creating that parallel code? The big messy block with SPMD, or just stick the little pragma in front of the for loop and you're done? So I think actually this work sharing construct, this loop work sharing construct, is extremely important. And actually for most people, that's all OpenMP is. They try and do everything in OpenMP just by splitting up loops. So we didn't say anything at all about how the loops are mapped onto threads. And that turns out to be a very important optimization. Not just take these iterations, compiler, in your infinite wisdom, and figure out how to divide them up among the threads and do a good job. As we all know, compilers are dumb. And it's very important that you think of compilers as dumb. Now, let me be clear, in case I have compiler friends out there. Compiler writers are smart. They're the smartest computer scientists out there. I couldn't write a compiler if my life depended on it. But the compilers they write are dumb. And therefore, you have to tell the compiler, split the loops up between the threads and do it this way. That's what the schedule clause is. So I go pound pragma OMP for schedule. And then the schedule gives information to the compiler, which says, here's how I want you to break up those iterations of the loop, package them up, and split them between threads. So let me walk you through the major schedules. So there's schedule static, which says pretty much exactly what you think. It means at compile time, figure out a closed form expression, that takes loop iterations and breaks them up into blocks and then parcels those out to threads. So I have schedule static, and then I can have an optional parameter for what chunk size to break them up into. So if I have schedule static alone, it says, give me one block of iterations per thread and hand it to the thread. So that's the example on that previous slide when I showed you the SPMD example of breaking up the threads, of breaking up the iterations. That would be schedule static without a chunk size. But if I put a chunk size, it says, take the blocks of this many iterations and parcel them out. So I may have chunk size 10. So if I have 100 iterations, chunk size 10, it's going to create 10 blocks of size 10 and then deal those out round robin to the threads. So that's how the static works. There's another schedule called dynamic. Dynamic's pretty cool. What it says is take the loop iterations and put them into a logical task queue. And then go off and grab an iteration. The thread finishes the work on that iteration, and then it goes back and grabs the next iteration. So now what it's doing is it's deciding at runtime, not compile time, it's deciding at runtime how it's going to break up work between the threads. Now you would do this if you had radically different work from one thread to the next. So that way, if one thread, when I ran it through one data set, took 1 second, the next took 20 seconds, and I run it with a different data set, it may be 5 seconds and 8 seconds. So this way you can adjust dynamically, not with some closed form expression. Once again, it takes an arbitrary chunk size. If you leave that off, it's going to do one iteration at a time. Or if I do a chunk size of whatever number, it will do blocks of those iterations. So scheduled dynamic 10 says break up the iterations of the loop into blocks of size 10 and then schedule them dynamically. There's a schedule guided, which frankly not a lot of people use anymore. But there was a paper long ago that said the optimum schedule is if you do dynamic and you start with a large chunk size, and then as you go along, you get smaller and smaller and smaller chunk size. So that's guided. As I said, it's not used very often. Static and dynamic are used all the time. Guided is not used as often. Then there's another option called schedule runtime. And what schedule runtime says is that you're going to pass in the schedule and the chunk size at runtime, either through an environment variable or through some runtime library routines. We use this a lot when we aren't sure which schedule is best and you want to try a whole bunch of them out. So this gives you an easy way without recompiling the program every time to try out different schedules. So that's the major use of that one. And then finally, there's a schedule called auto. And this is relatively new. Some of your older versions of OpenMP won't support this one yet. What auto says is, compiler, actually, I do trust you to be smarter than me on this one. Do whatever kind of magic you can think of to schedule this best. So it's giving the compiler the permission to be really, really flexible in how it does the schedule. So those are all the schedules, and I go through them all for completeness. But I just want to leave you with this. Most people only use static and only use dynamic. And to start with, only use static, only use dynamic. Keep the rest of those in the back of your mind to play with later. All right, now, when would you use these? So static I would use when the amount of work between iterations I can work out in advance. Remember, with static, you're making the scheduling decisions at compile time. With dynamic, I don't know how long the iterations are going to run. I have no idea. So the only way I can get a good balance load is to determine that at runtime as I run. So that's the time to use those. Now, there's another little detail about working with loops I want to go through. You notice again and again, I give you code like you see right here, where I go pragma OMP parallel, and then the only thing in that structured block is a pragma OMP 4. That's really, really verbose. So we support a combined construct, where I go pragma OMP parallel 4. Those two are exactly equivalent. It's just a shorthand. And it's actually very commonly used, because you can imagine there's a lot of times where I create a team of threads and the only thing they're going to do is work on a loop. So I can put the two of those together.